Hello, this is the IC Engine presentation for Group 1, consisting of Erin Mieth, Itzel Trejo, Andrew Williams, John Kim, and Annalise Young.
To measure the output produced by the engine, we make the assumption that the change in mechanical energy is done by external work. Therefore, if we find the torque applied over specific angular displacements, then we can find the work done by the engine's flywheel. In this experiment, the torque transmitted between the gears via the drive shaft is measured using a force transducer that holds the motor in place, and this force transducer must be calibrated in order for us to capture the device behavior as accurately as possible. Given the consistent vibrations in thermal expansion and contraction associated with the moving components within the IC engine, drift is expected, and therefore it is important to recalibrate the force transducer often. This drift is the reason why the force transducer calibration equations from week 1 to week 2 have different voltage offsets as illustrated in the figure, but their gains are roughly the same since the torque is dependent on the weights in the moment arm as seen in the tables.
In order to calculate the work done by friction, experiment was done without engine head to remove work done by air. A numerical integration was also used to calculate the work done by motor in steady-state angular velocity. In this state, the amount of work done by motor represents the amount of work done by friction and piston. The piston work is negligible compared to the friction value, as the frictional torque could be calculated in each cases of RPM. Angular velocity was calculated as well from measured values. As shown in figure here, the frictional torque value decreases as the angular velocity increases. However, since friction is always negative, we concluded that torque value increases as velocity gets higher. To acquire inertia of the flywheel, experiment was continued without engine head. The left plot shows the torque versus angular position of the motor. From the previous experiment, we have concluded that the constant part of the data represents the work done by friction. Constant torque was calculated from average value, which was 0.9035 Newton-meter. Therefore, the work done by friction was 175.5 watts, while work done by motor was 274 watts. Using the equation on the left, the inertia of the flywheel was calculated to be 0.019 kilograms meters squared.
We must now compare the theoretical to the experimental value for the flywheel moment of inertia to check the validity of our assumptions. We are given that the mass of each flywheel should be assumed to be 1.0141 kilograms, and the radius of each flywheel should be 0.07 meters, and we are to assume that each mass is a solid cylinder. Therefore, in theory, the moment of inertia about the central axis of each mass will be 1/2 mr squared. With 4 of these masses on the engine flywheel, we have that 4.0564 kilograms of mass will be added to the flywheel. Plugging that into the equation, we get a change in flywheel moment of inertia of 0.0099 kilogram meters squared, and that is the theoretical change. But, in using the equation shown in the third line, we actually get an experiment that it changed by 0.0094 kilogram meters squared. Now that difference is likely just due to the fact that our assumption assumes the masses are solid cylinders, when in reality they actually have a hole in the middle to insert on the flywheel, which will affect the mass moment of inertia of the flywheel. We must now consider the effect that adding the mass to the flywheel has on the acceleration of the flywheel. From theory, we know that if the same torque is applied by the motor in both cases, that with added moment of inertia to the flywheel, the angular acceleration must decrease to keep the torque constant, since due to Newton's second law, torque is equal to moment of inertia times the angular acceleration. And we saw that the moment of inertia decreased from 0.0289 kilogram meters squared to 0.0195 kilogram meters squared after removing the masses from the flywheel. This slide shows a graphical representation of the angular velocity with respect to time for the flywheel. So, on the left, it takes approximately 1.225 seconds to reach steady state angular velocity. That is with the masses added. However, with the masses removed, it takes only about 0.895 seconds to reach that same steady state value. So it can be seen that the angular velocity comes up to steady state quicker with the masses removed because there's a higher angular acceleration on the flywheel with the masses removed. And this is exactly what matches with the theory of Newton's second law.
The effect of changing RPM for the engine can be observed by plotting the torque versus angular position data collected during the experimentation process. Low RPM has a big difference to the medium and high RPMs. Noise in the measurements seems to increase as the RPM is increased. The first plot for low RPM provides an almost linear trend where the motor torque decreases as the angular position increases, up until around the 125 radians measure, where the torque comes back up before seeming to decrease once again. For medium RPM, the max value of motor torque increases as the torque reaches values of around 10.5 Newton meters versus the high of around 7.5 seen on the low RPM graph. The angular position max value also increases as the data is shown for up to 250 radians as opposed to 150 radians for low RPM. The trend of the plot is much less clear and is seen to oscillate up and down, potentially as a result of noise. Further filtering could help clear up the data. For the high RPM graph, a similar trend is seen. The range of the motor torque is not seen to increase, but the angular position range does increase to 450 radians. In all of these graphs, the torque seems to span values within a range of around 3 Newton meters, from 7.5 to 4.5 in low, and 9.5 to 6.5 in both medium and high. The motor has a fixed power output, so at lower RPM there will be a larger torque for the same power, and at higher RPM there will be a lower torque. The theory here seems to be supported by the data shown in the graphs. Now, the effect of removing flywheels on the steady-state operation of the engine can be analyzed as well. By removing the flywheels, we obtain the following graphs for different RPMs. The general trends observed in the last slide remain the same as we move from low to high RPM. However, important distinctions can be made. First, note the difference in low RPM, where values now go to 400 radians, and there is also a repetition of the pattern observed with the flywheel on. Second, with the flywheel on, the torque values deviated more from the average. Here, the torque values have a smaller range they span. However, there are more outlier values when the flywheel is removed. This might be attributed to a higher vibration of the engine and/or to the breaking down of modeling assumptions in this mode of operation. Looking at the assumptions that were made, a potential cause for error is the piston work being assumed to be zero. This assumption holds true for high flywheel mass or large ranges of numerical integration, but with the flywheel mass removed, the assumption is not valid and the model seems to begin to break down.
Before we look closer at the work impacts from the air inside the chamber, it is important to fully understand the 4 stages that complete one cycle of the engine. One cycle requires 2 full rotations of the crankshaft. In the first rotation, the chamber expands to let in air, and then valves are closed and that air is compressed within the chamber. In the second rotation, the chamber expands once again, valves are reopened, and upon contraction, the exhaust is pushed out of the chamber. Another way of looking at the process is using a PV diagram, as shown here. If you follow the arrows on the diagram, you can trace the process from intake to compression to expansion to exhaust and so on. PV diagrams are useful because they make visualizing the work done by a gas very easy. It's the area under each curve. In the compression stage, work is done on the air equal to the area under that section of the curve. However, in expansion, the air does work also equal to the same area as it retraces its path on the PV diagram. The total work done during compression and expansion is represented by the highlighted section on the figure, but ideally this sliver of work is actually close to zero and considered negligible. However, if during the expansion stage a jet of pressurized air were fed into the chamber, it would create an isobaric line segment on the PV chart, as shown here. As you can see by the new highlighted portion of the chart, this pressurized air injection would create a net positive work from the engine cycle that is not possible without the injection.
For simplicity of experimental setup and measurement collection, the work due to air and the work due to error are clumped together as seen in this slide in the orange box. The work due to error can be found by finding the difference between the experimental air work and model-based air work during each stroke, which is seen at the very bottom. Finding the motor work uncertainty is also very important when making conclusions about the accuracy of our model because it makes up the uncertainty bounds as seen on this slide. If the work due to error falls inside the bounds, then this means our sensors are not good enough and the difference between the data and model is large. However, if the work due to error does not fall inside the bounds, then this means our sensors are good enough. In order to find the uncertainty associated with the motor work, we must also find the uncertainty associated with the angular displacement and calibrated average torques. Therefore, making these three uncertainties particularly important when making conclusions about our experiment and model. Given that our error exceeds the uncertainty bounds as seen in the tables in blue, this means that for all the trials, with and without the flywheel and with differing RPM speeds, we can conclude that our model is inaccurate. This is mostly because the work due to error represents everything we were not able to model, as well as error due to noise and measurement inaccuracy.